Okay, we're back, Geography 212. For the second half of this chapter, we'll talk about tornadoes. And the slide starts off with a tornado thunderstorm connection. In other words, the only way you're going to get a tornado to form is out of a cumulonimbus cloud. Now, for the most part, you can see in the first bullet, they're going to be supercells. We get these terrific updrafts in these things. You can see at one point can reach 150 miles an hour. Let's just move on here. Let me get this up to, here we go. All right, now here's where the big updraft thing comes in. First of all, this is just a hypothesis. We're not really sure this is how tornadoes form, but this is one hypothesis. We get a strong westerly flow aloft. Okay, think maybe a cold front moving down with continental polar air, meeting maritime tropical air coming up from the southeast at the surface. Now, if you get strong winds opposing each other, one coming in from a relatively high altitude and the other one from a low altitude, you can see we're going to get this circular, almost rotor motion along the ground. Okay, but to turn that into a tornado, we need to get uplift. Right there. Now remember, we said in some of these supercells, we can get updrafts of up to 150 miles an hour. So hypothetically then, this could lift a horizontally rotating rotor of air into a vertically rotating column, a tornado. So again, this is just a hypothesis. It's very difficult to get information on these things. They're short-lived, they're dangerous to get too close to, and frequently these tornadoes are going to be completely obscured within the cloud or by heavy falling precipitation. One of the things, one of the forms of research that's going on right now, particularly out of the University of Oklahoma, is they have Doppler radar on trucks, and what they'll try to do is position Doppler radar units on opposite sides of a tornado, and that can build up a nice three-dimensional view of it. Now that's very difficult to do, and as I said, it's dangerous. We lost one of the world's foremost tornado researchers a few years ago named Tim Samaras, who unfortunately got caught too close to a tornado. Again, couldn't really see it because it was in the cloud, and got caught, and he and his son and one of his other researchers were killed in this tornado. If you're interested, National Geographic did a special issue on him a couple of years ago. All right, so that's one possible way they get going. But as you can see here in this diagram, these tornadoes can be embedded in the cumulonimbus cloud. You're not going to see them. So, I mean, how do we research them? How do we get close to them? That sort of thing. All right, look particularly over on the right-hand side here. This would be a plan view of where a tornado would occur inside a supercell. Again, you can see we've got the cold front coming out of the low pressure system. So we're going to have this sharp uplift of air there. And you can see a tornado curling around the backside of this low pressure system here. It's actually probably going to come in better here. Yeah, let's take a look at this one. If we take a look at this, is Doppler radar. So you're looking at falling rain. Now, high wind speed is going to swirl the rain around. So we can get some kind of this does give us a little bit of a look inside of a tornado. And if you look down here, this hook shape, we always see this hook shape of a rainfall pattern when a tornado has reached the ground. Now, a different type of Doppler over here, you can see the same thing here. You see this hook shape here. So the Doppler radar is useful in telling us when a tornado is on the ground. Our big challenge as meteorologists is to be able to forecast accurately when they're going to reach the ground. You can see this happens to be an F5 tornado. We'll talk about that in a minute, the Fujita scale. But an F5 tornado is devastating. It's the strongest tornado we record, and it's the F5 tornadoes that are the killers and the ones that produce a great deal of damage. So we really want to be able to predict the development of F5s, but we're not there yet. But again, just to summarize, the Doppler radar signature here of a hook can tell us when a tornado is on the ground. Can't forecast it, but it can tell us when it is on the ground, at least give people warning now. Where do they occur? Well, it's pretty obvious they occur east of the Rocky Mountains, and further south you go, you tend to get more of them. Ground zero, as it were, for tornadoes. You can see this area here, basically referred to as Tornado Alley. Now, why might that be? Well, this is going to be the meeting ground of continental polar air out of Canada, maritime tropical air out of the Gulf of Mexico. So we get these cold fronts coming down, causing sharp lift in front of the cold front, and that air that's being lifted is going to be very humid. This is going to create severe thunderstorms where tornadoes can develop. You can see we get very few, like I say, west of in the Rockies or west of the Rocky Mountains. And why is that? That's because there is no maritime tropical air in this area, or very rarely. So we really need that humid air to get sharply uplifted to produce a tornado. Now, we can occasionally get a tornado developing out of severe thunderstorm in Arizona or any place out west, but they are rare events. Arizona averages less than one a year. If you take a look at it, they average about one every 3 years in the state of Arizona. You can go ahead and read through this. One of the interesting points here is that in the United States, we'll tend to get about 1,300 of these things a year. I'm actually going to go back to this slide and talk about something else briefly here. The United States is where the world's most tornadoes occur. And if you think about it, the reason for it is if you go up here into Canada, there is a straight shot, in other words, no mountain barriers all the way down to the Gulf, and vice versa for the Gulf. A straight shot all the way up into here. So the point is, we can get continental polar air meeting maritime tropical air frequently, which is going to produce these things. If we went over to, say, Asia, that continental polar air from China and Russia cannot get down to the maritime tropical air that comes out of the Indian Ocean because of this very long, extensive range of mountains, starting with the Himalayas, the Karakoram, the Hindu Kush, and then even the Alps. So we have this formidable barrier to preventing continental polar air meeting maritime tropical air. So there are very few tornadoes in Asia. So by far the most tornadoes occur in the United States, and the second leading country where tornadoes occur is Canada, up here in the southern part of Canada, really for the same reasons they occur in the US. I've put a few links in here. You can check this out. There's probably tens of thousands of tornado videos on YouTube. So, I suggest you go in there and have a look at some. There's a couple of them, like I say, on here you can look at. They're pretty amazing. Okay, we have this thing called the EF scale. Now, the EF scale is new. It used to be called just the F scale. Let me talk about that a little bit. The F in the F scale stands for Fujita. Fujita was a meteorological researcher out of the University of Chicago who came up with this. What Fujita did was, because we cannot directly measure the wind speed in a tornado, actually think about that. How would you measure the wind speed inside a tornado? Well, look, first of all, you're never going to get to one. Rarely are you going to get to one. Secondly, it'd be too dangerous to do that. Third, any wind instrument you put in there is probably going to get destroyed. Tornadoes tend to be ephemeral things. They're only on the ground an average of a few minutes and they're gone. So to directly measure the wind speed, to get some kind of instrument in there, is virtually impossible. So what Fujita came up with is he would go into an area where a tornado had touched down after the fact. He'd take a look at the damage. Okay, so for example, he might see a 2x4 that's embedded 3 inches into an oak tree. So his question would be, what velocity speed did that 2x4 have to get to embed itself into a oak tree? So Fujita would go back into his laboratory at the University of Chicago, and he'd start, for example, in this case, start firing 2x4s into an oak stump to see what velocity was required to embed it that far in. And so basically he worked backwards. It was like forensic work. He treated these tornado places like crime scenes, and he wouldn't let anybody touch anything because you don't want to mess it up. So he spent years going back into his lab and recreating the speeds it would take to do this type of damage. He called it the degree of damage. So when we end up when I end up showing you here how the Fujita scale works, what we're looking to see is after a tornado goes through is a degree of damage that it creates. And then we can work backwards from there to estimate the wind speed of the tornado, which then puts it on the Fujita scale from F0 to F5. All right, let's take a look at this. All right. Let's start off. Well, actually, let's just take a look over here. The derived EF scale and the operational EF scale are pretty much the same. So Fujita scale then, the EF scale, we go from EF0, as you can see here, down to an EF5. And as we go from 0 to 5, the whirling wind speed is going to increase. So, in other words, actually, let's go over to the operational scale here. It's almost the same. So in other words, an EF0 tornado is going to have a whirling wind speed between 65 and 85 miles an hour. And you can go on up and see here. Look at an F5, have a whirling wind speed of over 200 miles an hour. Now, how do we determine if a tornado is an F0 up to an F5? Well, this is how we do it down here. Okay, these are called the damage indicators for all different types of places that can get damage from a tornado. So for example, let's say a tornado has gone through an area and damaged single wide mobile homes. We go over here, we click on that, and we get this information here. All right, so in other words, if you were the investigator from a single wide mobile home, you come over here and you go, okay, how far down did the damage go? In other words, did a unit roll on its side or upside down but essentially remained intact? And you go, yeah, because we didn't get any destruction of roof. None of this occurred down here. So we're going to end it at a degree of damage of 5. So we roll over here, and this is going to be your average between the low part of the lower branch and the upper branch. And let's just take the average of that. And that's going to be 98 miles per hour. So in other words, it took approximately an average wind speed in this case of 98 miles an hour to turn a single wide on its side or upside down. 98 miles an hour now is the figure we're going to use. We're going to go back up to this scale here, if I can get back to it. Yeah, and 98 miles an hour would put in the operational scale, puts it between 86 and 110. That would have been an EF1 tornado. That's how we know it's an EF1. All right, let's do another one. I'm just trying to think what. Okay, now this really happened several years ago. We had a tornado hit a hospital. So let's click on that one, and let's go down. I'll tell you right now, in this particular case, there was significant damage to the building envelope. In other words, some walls were destroyed, exposing interior parts of this hospital. So let's just say that's the way what we saw. There's your average wind speed. You take the low and the high and take the average, 210. So we're going to work with a 210 mile an hour wind. Go back to the EF scale. And what we're going to find here, we go back to the operational, that was over 200 miles an hour. So that was an EF5, okay? So anyway, that's how you do it. We go out after the fact, after the tornado's done damage, try not to touch anything, create the degree of damage for the type of unit or whatever that was hit, and do that. Now, I'm going to do one more here because this actually happened in Prescott a few years ago. We had an aerial photograph, and there was a report of a tornado in the Prescott area, and we have ponderosa pine forests around, okay? So that would be softwood, okay? A pine tree is considered softwood. So let's click on that. And what we found was we had a picture, we had a photograph of the aerial damage. And I can tell you right now, this is what it was. Trunks were snapped. So in other words, we had trunks standing, but they were snapped. So if we go over here, we find that that's an average wind speed of 104 miles an hour. And if we work back at 104 miles an hour, we can see that it was an EF1. So we have evidence that Prescott had EF1 tornado damage done to it a few years ago, okay? All right, well, there you go. There's your EF scale from 0 to 5. Here's how we find it out. It's called the degree of damage. So remember that. We do not actually measure directly the wind speed of a tornado. We go look at the damage it created, and because of Fujita's work over the years from the University of Chicago, we know what kind of wind speed it's going to take to create that kind of damage, and that's how we assign the F scale to it. All right, a couple of charts here I want you to take a look at. Let's start with the one on the left here. This is the percentage of all tornadoes between 1950 and 2012. Okay, so that's, 62-year period. That's a long period. Well, look at this. 76% of the tornadoes in the United States are either F0 or F1. That's 3/4 of them. So relatively, it's hard to say weak, but they're relatively weak tornadoes. Okay, 20% are F2 and F3. Okay, these are going to be more moderate tornadoes. But look at this, only 1% are F4s or F5s. The other ones we just haven't been able to figure out. So only 1% of all the tornadoes in a 62-year period in the United States were F4s or F5s. So you might think, well, who cares? Why should we be concerned? Well, why we should be concerned is with this graphic on the right side. If you take a look at all the tornado-related deaths in the United States, 67% have been from F4s and F5s, even though F4s and F5s only represent 1% of all the tornadoes. So this is the story right here. I mean, this is why we do so much research into F4s, particularly F5 tornadoes, because they're the killers. We have not gotten to the point where we can accurately predict when and where these tornadoes are going to occur. And until we do, we will keep getting events like this. Well, hopefully not very many. This was a horrific event back in 2011 in Joplin, Missouri, when we had an EF5 tornado for an extensive run across the city of Joplin, Missouri, and at one point hit the hospital. 158 people were killed, and the approximate amount of damage was $3 billion. This was a terrible event. If we could get to the point where we could forecast accurately something like this happening, well, we would have prevented some death, I'll tell you that. The problem is, if you get an F5 tornado hitting downtown in a town like Joplin, Missouri, you're going to get a lot of damage, okay? It was just, like I say, a horrific event. All right, that concludes the highlights for the tornado part in the chapter, so we'll talk to you later.